So now we're going to move on to the next speaker. So it's my pleasure to introduce Professor Dennice Gayme. So Dennice is an associate professor of mechanical engineering and the Carol Croft Lynn Faculty Scholar. Her research group focuses on modeling, analysis, and control for spatially distributed and large-scale network systems, which includes electrical power grids. So today, she's going to speak about enabling higher renewable energy penetration through modeling and control. So thanks for speaking, Dennice, and I'll turn it over to you. Dennice, unfortunately, I think you're muted.
Is that better?
Yes, we can hear you now, but can no longer see your slides.
That's okay. That I can fix.
Great.
All right, we're good now? Okay.
Good.
Sorry about that. This is what happens when you have new technologies that you're working with. So the annual energy consumption right now is about 11% renewables, and that's over all of the energy sectors. So we typically think about energy in terms of electric power, but there's also commercial, residential, and industrial, mostly heat and air conditioning, and transportation. So when we think about renewable energy, most of the renewable energy is going to electric power. So if you look at renewable energy and the different sectors, you can see in gray here, especially in 2018, most of it is going to electric power. And in fact, renewable energy is really rapidly growing. So the renewables were the largest capacity additions in 2019. They were also the largest capacity additions in 2015 and previous years. So they're growing at a rapid rate in the US. So wind was about 46% of that, at least planned in 2019, solar about 18%, and then some lower numbers were the natural gas, which is also continuing to grow. But this is in comparison with retirements of things like coal and older types of natural gas and nuclear energy. So this is a really great picture if you care about sustainability, because you can see that these sustainable sources are really growing. But as you often hear, there are some major challenges associated with solar and wind, which, as I just showed, are some of the largest sources of renewable energy. And you often hear the words variable, intermittent, and uncertain associated with these, and this is really what people mean when they say that. So if you take a look here at the left, at the top, you can see a plot of wind energy output for a wind farm in California. This is in Tehachapi. And so you can see every line here represents 1 day of wind farm power output data. So you can see some days, you look across the top here and you get very constant wind power output. Other days you get very little output, but in many days you get these precipitous drops that happen very suddenly. And if you look at the average power output over the month, which is this blue line sort of towards the bottom here, you can see that it in fact is not very connected to what you see on a daily basis. Similarly with solar, if you look on the right here, you can see a clear day. This is some solar data from Germany. You get a very well-defined peak in the middle of the day when there's a lot of sunshine. And a cloudy day, you don't get a lot of solar energy. But most days, especially if you live in Baltimore, are very variable. So half an hour, you can see lots of sun, 20 minutes later it's pouring, or at least that's my experience of Baltimore. So you really can't predict that. You get a lot of variability. It's very intermittent. It cuts out in and out, and it's uncertain because the forecasting technology is only so good. The other thing about renewable sources that are difficult to deal with in some sense is they're location dependent. So here on the bottom left, you can see a plot of the US where in blue you see where the majority of the wind resource onshore is located. You also have a lot of wind resources offshore on the Pacific and Atlantic coasts. And then you see where the people are located in red. And so you can see that there is a disconnect between where you have population centers and where you have large sources of wind energy potential. And you can see that this corresponds to, in the plot on the center of the map, where most of the wind farms have been built historically. So you can see there's a lot of green in the middle of the country here where we have large wind resources, and those are again are not perfectly aligned with the population centers. Similarly with solar energy, so here on the bottom right, I'm showing solar potential in the US. You can see in the Southwest, there's a lot more solar potential, as well as in Florida, which does align with some of the population centers, but not the population centers in the Northeast. So you do have certain problems with these resources that you need to be able to overcome in order to use them most effectively. And so one of the big problems associated with this is when you think about the power grid, it's really just a giant circuit. So if you look here on the left, you can see my schematic of a power grid where you have some sort of generator, you have transmission lines where that carries that electricity to different types of distribution. So say this may be a factory here, you may have a city, and you may go all the way down to residential areas. You can think of that generator as this battery, and the electricity is flowing to these loads, which are the heating or air conditioning loads in these places, as well as lights and other things like that. And so because it's really a giant circuit, and that's exactly how one would model it, it needs to obey circuit laws. And so these circuit laws are laws of physics that govern the behavior. And so in practice, what does that mean? Well, it really means that the generated power has to equal whatever the loads are, plus whatever losses you have in these transmission lines and other aspects at all times. And that's a very difficult problem to overcome when you have very intermittent or uncertain resources and you have variability in the system. So there's a lot of ways people have looked to overcome that, and that's one of the main focuses of my research. So a very naive or static way of looking at this, and so this is a picture from about 15 years ago, where the idea was, well, typically in places you have a lot of wind at night, solar during the day. You can balance solar and wind sort of statically by thinking about having enough solar to balance the wind that you don't have in the middle of the day and enough wind to balance the solar that you don't have at night. And then you can build up an entirely 100% renewable power system by building in some high certainty renewable resources like geothermal, biomass, and small hydro. So this is a picture from the California Independent Power System Operator, some work out of Stanford that looked and said, well, you can actually, if you have the right mix of resources, track a demand that looks like the top of the signal here. But in order to do that, you need really good resources for forecasting and both supply and demand side. And this idea of forecasting on the supply side is very difficult because of forecasting the weather and the resources, but it's also difficult on the demand side because you have customer behavior that's coming into this. You have electric vehicles, which are changing load patterns in various places, and you even have demand response or load management programs, which allows people to adjust their electricity use based on current prices that are also changing some of the load patterns. So this type of static forecasting can be very difficult, but there is a lot of research that is improving these things every day. So one of the things that I focus on in my research is adding additional flexibility. So one way, and the way that's most often discussed, is adding grid integrated storage. So if you think of this system, you can add storage either near the generation, so you can combine storage with a wind farm, or you can put storage near the load. And typically you put storage near the load because you can think of maybe at night you have a lot of wind power, you want to get it close to the load for the peak demand time, when maybe you don't have as much transmission capacity to get it from one side where it's generated to the other. So you have the storage closest to the load. It eases congestion in that way. And storage comes in a lot of forms. It's not just the batteries, the lithium-ion batteries that we think of. You can also have pumped hydro, which is actually a source of storage that's very popular in Europe because there's a lot of mountains. So you have a lot of grids in Europe that are balanced because of the Alps. And trading power that way. You have short-term storage from mechanical things such as flywheels that can be spinning and take up short-term imbalances. Solar thermal energy actually uses thermal storage. So there's various types of storage that we can use in the system. Another way to add flexibility is aggregating small resources. So this is another area that we work on where we try and take things like electric vehicles, residential PV solar cells, maybe a Tesla Powerwall or something that people have at home, air conditioning loads, hot water heaters, smart refrigerators, and aggregate them into what we call virtual batteries. So you get this large source of flexibility by aggregating all these resources. There's benefits in this aggregation, not only because you have a larger resource, but also because now you have added privacy. It's not that I know I'm controlling X person's water heater, I'm controlling a large group of water heaters. So it gets rid of some of the privacy aspects of controlling small DERs. And then you can build those up and use these small aggregated battery, flexible battery resources all through some sort of feeder system, and then use them as larger resources in your energy grid. So that's another way that you can do that, but you need good sources of models and control in order to do that. The other thing you can do is think about controlling the resource directly. So in a situation where you maybe have better forecasting technology for something like wind, you can start to think about obtaining accurate predictions for the wind farm power output over some range of conditions, either short or long term, depending on how good your forecast is and for how long it goes. And then also having wind farms, because they're quite large, participate in some of the energy markets that you have. And how do we do that? Well, we do that by looking at what's important in creating small reduced order models of these systems. So if you look at this simulation, oh, that didn't work. So if you think about this, you can look at a wind farm. And so this is a wind farm that's being simulated by my collaborators group, Professor Medivo, where we're looking at these blue areas behind the turbines, which are the wake regions or the reduced velocity fluid that comes after you suck the kinetic energy out of the wind to get the power out of it. And what we look at modeling is how these wakes grow, develop, and interact with one another. And if you do that, you can get a better sense of how much power potential you have in a farm. And you can also move these wakes around a little bit by controlling the amount of power you take out at one location versus another in these large farms in order to do things that help the grid. So if we then model this complicated system, we can do things short term like power tracking. So this is showing a power tracking signal that's used to create the supply balance, demand balance on the grid. So this signal is in red, and in black is how we're tracking the signal. And the gray shows what would have happened if we didn't control the wind farm. So on a short-term basis, by using these advanced controls and models of the wind farm, we can actually use the wind farm that was leading to variability to help reduce the variability in the system. But of course, this does require good forecasting. So I'm going to stop there and just leave up this slide. If you're interested in this work at Hopkins, Professor Machada, Professor Medivo, and Professor Hobbs, whose names and departments are listed here, all do this type of work, so you can contact them for more information or take a look at their websites.
Okay, well, thanks so much, Dennice. All right, great stuff. So I'm going to, again, encourage the audience to enter your questions into the Q&A window. And I do have one question from the audience here. So, Dennice, we'd love to get your thoughts on how optimistic you are that technology will help us to meet the global greenhouse gas reduction targets in the years ahead. So especially in the not too distant future, what's coming out soon versus 10, 15, 20 years out?
So the types of technology I work on are more at the level of control and aggregation. And I think we need a variety of both types of technology. So we need better wind turbines, we need better, solar PV cells like Susanna makes, but we also need ways to integrate and control them. So I think there's been a lot of really good research showing that it's really possible to integrate more and more of these renewable sources if people are willing to invest in the technology and the research before they build these things. So one of the things that happened with wind farms is that people built a lot of wind farms, were really excited about the technology, and then later found out that there could have been better ways that they would do it. And so they ended up not getting as much power out of these wind farms as they expected, which led to this underperformance problem, which was really just building something before you understood how it worked problem. And so I think we really need to put the research in order to do this right, in order for these things to really take off.
Great, thanks. So I actually have a follow-up question on that maybe, which is, what's the role, what's the role of the smart grid that we hear about in this, and where is the United States on developing any kind of infrastructure you could call a smart grid?
So I'm a bad person to ask because I really hate the term smart grid. And most of the people I know who work on power systems don't like it either, because it implies the grid we have right now is dumb. And it's not, right? I mean, it works amazingly well given how old it is, but I think the idea of a smart grid was really having more sensing and having more control in the grid. And really small changes have made that happen over time. So we're really far along, because maybe, definitely 10 years ago, if your power went out, the utility didn't know where the power outage happened until they got enough phone calls from people to say, okay, the tree must have fallen here because everybody on the other side is who's calling me. Now we have meters that send back information and say there's no power. So this seems like a really low-tech thing, but it's actually making our grid smarter and making the ways we control and manage it a lot smarter. And that's enabled things like cycling your air conditioner as well.